John here, and we started thinking of ways that the Center for Ethics and we can do cooperative work, because I know people in faith communities are often very interested in ethical issues, and probably there is no more pressing ethical issue, or at least it's up there as with the top ones, is global climate change. And so Jen and John and I and other folks in the, let me get the name right, Western Montana Spiritual Development Council worked together to put this, and I have to say they carried most of the weight on this particular project. So thank you for coming, and we hope we'll have some really good conversations and be able to educate ourselves and learn a lot about this important issue. So thank you again.
I just want to welcome you from all of the congregations in Missoula that have joined together to become the Western Montana Spiritual Development Council. We're a fairly loose association of people. A lot of you have been to meetings that have sponsored programs like Jim Wallace and David James Duncan, and we're just delighted to be part of this collaboration with University of Center for Ethics to try and bring this issue to our own congregations. You should know we're being paid by MCAT, yay, MCAT. And we hope to make the DVDs available so that you can use them for adult education classes once they're done. That would be through the library, so it wouldn't cost you anything. This is going to be free, these 5 talks. If you want to give us a small contribution so that we can pay for the wonderful room we're in, we'll gratefully accept it, but that's not required. And again, we just want to welcome everyone who's here. Okay?
My name is John Lund, Lutheran Campus Ministry. I'm the Lutheran Campus pastor. It's been wonderful working with Dane Scott from Center for Ethics and with a number of people from the Spiritual Development Council. As we've been thinking about climate change issues, usually the conversation happens with faculty and with scientists. There's been a number of presentations in town and on campus. If we're paying attention, we could have caught any of those. Or it happens in the political sphere or perhaps in the media, but it's really difficult to talk about it in our faith communities often, in parishes. It's political and it's controversial and we're not sure about it, and it's often hard to be a community that is talking about difficult issues, and this is a difficult issue of our time. And so part of our charge in this program is to say, how can we bring this issue to light with all of the complexities and talk about it as people of faith, and how can we bring these conversations back into our faith communities? So that's what we're about, what we're trying to do. We couldn't do it in a night or even in a weekend because there are so many elements to it. Tonight we're just going to go with the science, and Faith Ann will do a wonderful job with that. Next week, Dane Scott will look at the ethics and the justice issues that come out of climate change on a global scale, and how that will affect many people and affect us. The week after, we have Steve Schwartz, who will look at how it gets talked about. What is the rhetoric in the media, in the politics? How do we talk about it? What has been the history of the rhetoric, and how does that affect the way we engage with it? As people of faith, another question is around how we understand our relationship to God and our environment, and that's a theological question. I will address that. And then we have Albert Borgman, a philosopher, talking about practices and a spirituality that goes along with this. And then at the end of all that, in early November, on November 10th, we'll have a Saturday morning workshop, and that will be with Jesse Dye, who is from the Earth Ministry in Seattle, and the title there will be Faithful Advocacy for All Creation. And her work is, how do we engage as individuals, as communities, and in a broader scale? What is effective? What can we do? And how can we make a difference? And so that will be the end of the series, Saturday morning workshop. So that's our plan. If you come to any of them, that is wonderful. If you can make the ones that fit in your schedule, come as you are able. The other piece then is to also engage in conversation, so that we'll have the presentation, but then we'll talk around our tables and then come back and talk as a whole group. And so we'll do that tonight, and we'll have that model as we go through this whole series. So again, thank you for coming, and I want to introduce Faith Ann Heinch, who is a environmental physicist and is working in the area of climate change and has been looking at the science very hard and over a long time. And thank you so much for being here.
Thank you very much for inviting me here. It's a pleasure to be able to present something that is quite important to me in both my personal life and also my scientific career. So hopefully I'll be able to impart some of that to you. As Pastor Lund said, we will be talking only about the science tonight. So any of the implications beyond that are for the next few weeks, and I would like to focus on the science. If I go too fast, which I have a tendency to do, my students will back me up, just let me know, I will slow down. And if I start belaboring a point that everybody gets, you can tell me to speed up too. That's quite all right. Okay, I've tried to pare it down to the bare essentials, but I'm still not certain I made it within the time constraints that they gave me. We'll see how it goes. Okay, so the title that they gave me was, Is Climate Change for Real, and Can We Trust the Science? And I kept that title because it brought up an interesting dilemma for me, in that as a scientist I say, well, duh, of course we can trust the science. But the aspects of science that we can trust, I think the question that as I interpreted later was, okay, how certain are scientists about this issue? And then, is climate change for real? I hope to be able to answer by the end of the night that the evidence shows that it is, and that humans are in part causing it. So a lot of the information that is out there in the world comes from the Intergovernmental Panel on Climate Change. And this is a group of scientists from around the world who every 6 years get together and over the course of about a year or a year and a half actually develop the most comprehensive study of climate change that can happen. And this group started in 1988, and there's been 4 assessments. The most recent one came out beginning in February of this year, in 2007. And the function, again, is to provide assessments of the science of climate change. And the scientific community, people from all over science, contribute to this. And they're all scientists. Then another interesting fact, 75% of the authors that were in the current assessment did not participate in the last assessment. So we got fresh faces involved and analyzed the data. The requirement is that the material has to be peer reviewed. So if it's going to be considered for this, it must be in the peer-reviewed scientific journals, and it has to stand the test. So that's also another thing that people bring up is the summary for policymakers. And if you may or may not be aware, but that goes through a really rigorous word-by-word tug of war between government representatives from around the world and scientists. And so ultimately, though, the scientists are the ones who put that together and defend the science. And this last time, there was few changes made, and the science as a whole stood pat the way it was written. So originally, 2,500 scientists took part in this. 800 of them wrote the report. The remainder of them were participating in the review process. There were 450 lead authors, including Dr. Steve Running from here on campus. 130 countries were represented, 6 years of work by the time all the computer models were run, and ultimately 1 report, and that was produced this year. The final, there are 3 working groups involved. The final working group has not yet submitted their final report, but it's very, very close. Okay, now on to the science. I've bored you with the technical aspects. Okay. The first thing to understand is the difference between weather and climate. We hear a lot, we can't predict the weather next week. How are we going to predict the climate in 100 years? And the answer to that is that weather is a very chaotic system. It lasts on the order of the next day to possibly the next month. When I interned with the Weather Service about 15 years ago, gosh, it's been a long time, we could forecast 3 days. And now they're up to forecasting about 10 days with relative accuracy. And that's really about the outer bound of what they'll be able to predict in terms of weather. And I'll explain why in a moment. Climate, on the other hand, is the average of the long-term conditions over years to decades. We know that in the spring, the ground starts to thaw and it starts to warm up, that the summer tends to be hot, and that the winter here in Montana tends to be cold with snow. And we can predict these things year after year after year because climate patterns are somewhat predictable because they are longer scale and they're not as chaotic. Okay? Another way of looking at weather and climate is that weather is choosing whether wear shorts or long underwear on your way to any given meeting. The ratio of shorts to long underwear in your drawer is considered climate. Okay? I thought this was a really interesting way to put this, and I borrowed this from Deborah Williams from Alaska, and this was 1950 in Alaska. Okay, a lot more long underwear than shorts. In 2007, they're buying shorts a lot more than they are the long underwear. Okay, so this is weather and climate. Another way to look at it is, I'm sure many of you were here during Mount St. Helens. I wasn't, but it was one of the events that determined that I wanted to go into science because I thought that was just cool. Okay, and in 1980 it erupted, and the ash cloud took 10 days to go around the world. And that's about the memory of the atmosphere, is 10 days. And this is why we're not going to be able to predict weather much past that, because beyond that, your atmosphere just doesn't have a memory. Okay, but climate involves much more than the atmosphere, and the memories are much, much longer. A lot of the science started in 1958 when Dr. Keeling started measuring CO2 concentrations in the atmosphere at Mauna Loa in Hawaii. And Dr. Keeling had a home here in Hamilton, and he recently passed away. He was a wonderful, wonderful man and an expert in his field and a very, very meticulous scientist. And they took measurements every month of the year, getting the CO2 concentration at this site. And what they noticed over time is that the CO2 rate is increasing. And not only is it increasing, it's increasing at a faster and faster rate. Okay, so the overall trend is to increase. These wavy lines in between are your seasons. If you think about what happens in the summer when the trees are out and they're photosynthesizing, they take CO2 out of the atmosphere. And in the winter in the northern hemisphere, when the trees are dormant and we're releasing more fossil fuels through heating our homes, there's going to be much more of a release, both from the environment and from our heating. And those two things together are going to lead to dips in this atmospheric concentration in the summer and peaks in the wintertime. But both the dips and the peaks are getting higher and higher as time goes on. Okay, this leads us to the fact of the greenhouse effect. And this was first devised by John Tyndall in 1859, I believe, who discovered that he was the one who experimentally proved that CO2 would absorb heat. Okay? This was taken further by Svante Arrhenius, who was the first one to propose the greenhouse effect itself. And the greenhouse effect is that the sunlight comes into the earth. Some of that sunlight is reflected immediately, but some of it stays here, both on the earth, absorbed in the earth, and in the atmosphere itself. CO2 is called a greenhouse gas because the more CO2 there is in the atmosphere, the more heat it's going to absorb, and it's going to keep that heat closer to the surface than actually leaving the atmosphere. So we've got more heat sort of trapped near the surface, okay, because it's staying in the atmosphere and it's not leaving. Okay. This is fundamental to the concept of climate change because any of your greenhouse gases are going to do this, including carbon dioxide, methane, the CFCs that we used to use to refrigerate in our refrigerators and in our automobile air conditioners. So all of these things, when they're in the atmosphere, are going to absorb heat. CO2 lasts in the atmosphere about 100 years. So the CO2 that we emit now is going to impact us about 100 years from now. Okay. And the more CO2 we put into the atmosphere as we go on, the longer and longer we're going to have an impact. So these are not short-term impacts we're looking at. These aren't weather impacts. These are climate impacts. The CFCs that we look at, those last thousands of years in the atmosphere. Fortunately, we've reduced or eliminated the use of those successfully because of the ozone hole that was discovered in the 80s. And those, while the ones that are in there are still there, there are a few, we're not adding substantially more of them as time goes on. We are, however, adding significant amounts of CO2 and methane. Okay, so where does the CO2 come from? Does it come from land or does it come from people? And the question is that it comes from both, but humans play a role in both of those. Okay, the first one is the land use change itself by converting to agriculture is releasing greenhouse gases into the atmosphere. The other one is through the burning of fossil fuels, we are also releasing CO2 into the atmosphere. And we can tell that it's coming from fossil fuels because if you do a chemical analysis of the CO2, you can actually tell if it's coming from current plants or if it's coming from plants that were laid down as part of the fossil fuels. Okay, so we know that it's coming from, most of this increase is coming from the fossil fuels. Okay, so how does this impact temperature? Well, if you increase the greenhouse gases in the atmosphere, the physics behind that demonstrate that you should also increase temperature. And in fact, we've seen as time has gone on and CO2 has increased, we are increasing temperature and temperatures increasing more quickly. These are global mean temperatures, and the warmest 12 years record of the warmest 12 years globally, 11 of those have happened in the last 11 years. Okay, the outlier there is 1990. Now there are some years in the past, for example 1934, that was the warmest year on record in the United States. But globally, it wasn't, it's down in this area, but it doesn't come close to the global temperatures that we're seeing nowadays. Okay. When we talk about computer models, we're looking at, can we explain what's going on in the atmosphere? And this is an example. The red are the observations of temperature change that we've seen, and the gray is how the model does. If we only look at natural forcings and we ignore human impacts at all, we can't match what we see happening. However, if we add the effects of humans, we get a much, much better fit to what's happening in the atmosphere. And these models can improve. They're not perfect by any means, and they're improving all of the time. Okay, but we can still do a reasonably good job of matching the observations with what's happening now. One of the reasons that climate has such a huge memory is because of the oceans. A lot of this heat is absorbed into the oceans. And the ocean circulation, it can take 1,000 years for that heat to move through this entire system and then come back out into the atmosphere. Okay, so the ocean has a very long, long memory. And this is one of the reasons that we're concerned about climate change as well. 90% of the heat balance of the climate system comes from the oceans, while only 3% comes from the atmosphere. Okay, so when we're looking at this, the oceans are going to play a huge role in what we're doing in the future. If we look at sea surface temperature then to try to find out what happens in the oceans, we find out that over all the oceans, there have been increases in sea surface temperature. Now, some of them have been quite small increases, like in the Antarctic and equatorial Pacific. Other places, like the North Atlantic, have been quite substantial changes. But everywhere, there's been an increase in sea surface temperature. And since this is heat that's been absorbed by the oceans, this is going to be around for a while. Because of the heat expansion, because of the heat, the oceans are expanding. And this is most of what's causing the recent sea level rise that we're seeing. And in addition, we're having melting glaciers and ice on land that's melting, and that is adding to this. But for now, almost all of this is actually coming from just the sea warming up itself. Okay, but sea level is rising, and this has great impacts around the world as well. One of the questions that we get a lot is, what about hurricanes? Because Hurricane Katrina 2 years ago, and then we had 2 major hurricanes this year that didn't fortunately hit the United States. But what about that? There doesn't appear to be any evidence that there are more hurricanes right now. Physically, there should be. As the oceans warm, the oceans are providing the energy for these strong storms. And as oceans warm, they should provide this energy, and they should lead to increased number of hurricanes. But we haven't seen that. Okay. What we have seen, however, is the strength of the hurricanes is increasing in response to the warmth of the temperature of the oceans. So as we get, when a hurricane develops, it's liable to be much stronger than before because it's got this energy waiting for it. Okay. Another thing that we're seeing out there as additional evidence is that the Arctic sea ice is getting thinner. Arctic sea ice used to only be about 6 meters deep. Okay. And nowadays, it's about half that. We've lost about 30% of that, actually. And so Arctic sea ice is getting thinner. It's not as thick as it used to be. In addition, it doesn't cover as much area. So not only is it getting thinner, but it's not covering significant portions of the area anymore, and that water is then entering the oceans. Now, this is not going to contribute to sea level rise because this ice is already in the water, and it's just replacing itself. Okay, so this doesn't contribute to sea level rise. Okay, on the other hand, Greenland melt has been extensive throughout time. And if we look at the melt extent, this light pink here shows how far Greenland melted during 1992. And then in 2005 shows the dark red. So it melted all the way up through here. Now, when that water melts and goes into the ocean, it is going to contribute to sea level rise. And what we see over here is called a moulin, and this is actually how the ice melts. The ice melts, and then this meltwater actually goes through the ice within the glacier itself and actually speeds melting of the ice. So it's kind of a positive feedback effect, where it's going to increase the melting in response to already melting events. In Alaska, if we look at the glaciers, there are a few glaciers who are increasing in thickness, but by and large, these glaciers are all retreating. Okay? And these are off the scale here because their order of magnitude is almost double that of these other glaciers. Okay, so the majority of the glaciers in Alaska are retreating. In Antarctica, we've got some glaciers that are increasing in extent or depth, but most of them are decreasing. And if you add it all together, there's still a net loss of ice from Antarctica as a whole. So both the Arctic and the Antarctic are responding to these changes in temperatures by melting. If we come closer to home and look at Shepherd Glacier and Glacier National Park, we can see the difference between 1913 and 2005. And they estimate that by 2030, most of, if not all of the glaciers will be gone from Glacier National Park. So we can see these changes even within the course of our lifetime. So how is the biosphere responding? That's the science, that's the evidence that we have for climate change. How is the biosphere itself responding? First, the good news. Growing season length is getting longer. Now this is 5 decades of data, and this is about 1.5 days per decade. So we've got about 7 days, 7.5 days extra of growing season here in Montana than we had before. This means we don't necessarily have to ripen our tomatoes in the closet in a paper bag. Okay? California, over 5 days per decade, at 5 decades, that's over 25 days. This can be quite substantial. Okay? Some parts of the country haven't changed very much in the length of their growing season. Okay, the darker red means the more sure we are about the data. Okay, overall, the U.S. has changed by about 10 days, lengthened the growing season in the U.S. Okay, also, if we look around the world from 1982 to 1989, the green represents areas where growth has increased. And this has happened in large parts of the world. We've seen since then that this trend may be changing, but this data indicates that at least for now, the plants appreciate the extra temperature, okay? But on the flip side of that, with increasing temperatures and we come to increasing spring runoff, and we have our snowpack for less time. And this has led to a western fire season that's about 78 days longer than it used to be. Okay? There's been a 4-fold increase in fires that are greater than 1,000 acres, a 6-fold increase in the number of acres burned, and a greater increase in forests above 6,500 feet. Okay, so these fires are occurring, they're larger, they're bigger, and they're going higher than they have before. And this is in part due to the fact that our systems are so dominated by their impact, by snow impacts. And if you have warmer spring temperatures, you're going to have less snow in the late summer. These are just some satellite pictures that we have from some of the major fire seasons. We have 2000, 2003, 2005, and 2007. We can see the impacts that the smoke has on the areas around them. Okay, this is a space shuttle picture of Montana on August 13th. And this points out where Livingston was. Now, some of this over here is cloud, okay? But a lot of this in here is just the smoke cloud that we were breathing. And we all remember that. When they studied this, not only was it important to understand how much more the forests were burning, but also why. Because we have had 100 years of active management of fire, and this could have an impact as well. So they further did a study to find out what relationship there was to climate. And what they found was in years with an early spring melt were also years generally with large fires. Okay, because it lengthened the growing season again. Okay, and this just shows the number of acres burned in any given year. Here's 2006. This dark brown here is 2005. The green, if you can see it, comes right up here. That's 2007. And the season's not quite done yet. They carry this through October 1st. Okay? And the blue is the 10-year average. So 2000, 2005, 2006, and 2007 have all been above the 10-year average. Okay? Another thing that we need to be concerned about are bug infestations. And what we found on it would be your right-hand side, is the climate suitability classes. The more red, the more suitable it is as for pine beetles. And we found a correlation there also then with pine beetle attacks. And there isn't peer-reviewed papers yet to show this, but we have found that pine beetles, instead of having a 2-year cycle like they used to have, a 2-year life cycle, they've reduced that now to 1 year. The growing season's long enough that they can complete their life cycle within 1 year. So there's a good chance that we'll see more of that in the future. So what's going on in the Pacific Northwest? And I include western Montana in that. Okay. First off, sea surface temperature. We see a rise in sea surface temperature off of Victoria, Washington, just like we saw globally. If you look at at the trends in this area, there's annual variability in here, and here's 1934. But overall, there's a trend upward, an average of 1.5 degrees Fahrenheit during the 20th century. Okay? If we convert that to records by station, all of the red stations have shown warming. And the smallest circle is not quite a degree Fahrenheit, and the largest circle is a little over 3.5 degrees Fahrenheit. So there's been quite a bit of warming around here. There are some exceptions in here, most notably Anaconda for us. And but overall, there's been a trend towards warming in the area. And on April 1st, it used to be March 15th, the scientists would go up into the mountains and they would measure snow water equivalents. How much water's in the mountains? And this helped them judge what the water supplies were going to be for the year. I'm sorry, it used to be April 15th. Now they've pushed that back to April 1st. The reason being that there's been a substantial decrease in the amount of water available on April 1st. And they're talking about moving it back to March 15th, if they haven't already, to go up there and find out the equivalents. And that's because there's been decreases in the amount of snow still on the mountains at this date. Okay, if we look at the trend across 50 years, it's been this red circle, which corresponds to this red circle here, is 20 days earlier melting. So on average, snow melt is coming about 20 days earlier than it did before. And if we look closer here in Montana, we did an analysis in our lab to find out what's happening. Now these are mean March temperatures. And all of the temperatures in Bozeman, Billings, Kalispell, Great Falls, and Missoula have increased in 50 years. In Missoula, this increase is 4.5 degrees, 4.6 degrees Fahrenheit in March. Bozeman's the biggie. at a over 7.5 degree increase in temperature in March. And we can see this when we go outside in March and we wonder where the winters are. I moved here 5 years ago, and I've been told I've never had a real Montana winter, which unfortunately was one of the reasons I moved here. So I'm a little disappointed, but I keep hoping this year we'll have one. The further impact, though, is once snow starts melting, snow reflects energy, but the ground beneath it absorbs it. So the more that snow melts, the more ground there is to absorb heat, and the faster the remaining snow is going to melt. So this is another one of those feedback effects that we see with less snow melt, or less snow actually is going to mean more snow melt and less water later in the growing season. Okay, if we look at annual mean temperature, things are a little bit more mixed. Great Falls actually has a very slight decline. Missoula increased by about 1.8 degrees, and Bozeman is up right at 2 degrees Fahrenheit. Okay, so annually the increase hasn't been as great as in the spring. Okay, spring seems to dominate the annual signal. If we look at precipitation on an annual basis, this is one of those areas that we're least confident in as scientists. What's precip going to do in the future? Well, when we see graphs like this, no wonder we're confused. There doesn't seem to be any real trend to the amount of precip that's happening. Okay, so we got a little excited and we investigated a little further and we said, well, let's look at snowfall. What's snowfall doing? And we find decreases in snowfall at every location around the state. Some of them are quite substantial. So there is this approximately the same amount of precipitation following, less of it is falling as snow. Okay, and that leads me to when we try to figure out what's happening in Montana, the main issue is going to be where's the water and when does it fall? So what's happening to our precipitation? If our precipitation continues to fall mostly in the winter and the fall through the early spring, and it's falling more as liquid rainfall instead of snow, then we're going to see some issues where we're going to run into a negative balance. And this could lead us to things that we've already started seeing, like increases in wildfire, forest mortality, low stream flows or stream temperatures that lead to stream closing and cutting off that fishing that we all like to do. We'll see lower productivity. This NPP is just a measure of productivity. We're not sure what's going to happen to biodiversity. And we're also not sure what's going to happen to invasives. And what are we going to define as an invasive versus something that's just a climate, just moving in response to climate? Some people are calling them climate refugees. So knapweed, I think we'd all agree, is an invasive. But there are things that are moving, particularly in Utah. We have more shrubs moving into areas that didn't have them before. Well, is that in response to climate? Or is that something where they're actually being invasive? And these are difficult questions. On the flip side, if our precip tends to fall more throughout the year and not just in the spring, so we have summers that are actually wetter, then we're looking at higher productivity, higher stream flows. We still don't know what's going to happen to biodiversity because we'll have warmer temperatures, but we might have more precip, so other plants might be able to outcompete natives. We could improve our wildlife habitat, but then we come to the negatives that I kind of threw in the middle here to throw you off and see if you were looking. We've got stream bank erosion, insect-borne diseases, and human health issues. So either way, we're going to have issues that we're going to have to deal with. They may not be the same issues we've had to deal with in the past, particularly here in Montana. And it's not going to depend on temperature. Temperature we know is going to continue to increase. The thing that we don't know is what's going to happen with precipitation, and that's going to determine where we are on this graph. Okay. One thing that we see here is that currently, if you look at the Dalles in Oregon, and this has been corrected for the dams, and I have to admit I don't know how they did it, but they took the dams into account, and this is naturalized flow, and our peak flow tends to be in June. In 2050, they see that peak flow coming about a month earlier, which is going to lead us to having less water available in the summertime, okay, in our streams. And if we look in Montana over time, we notice that the mean daily statistic is the brown here, and the blue is the current daily mean discharge, and we're below the mean throughout this time period of 2003 through 2004. And this is just an example graph that we were able to find. This continues on through present day. By 2050, global climate models project Montana to be 5 degrees Fahrenheit warmer in the summer, but receive 10% less rainfall in the summer. Then we're going to have to deal with issues of recreation versus agriculture, because we're still going to want to eat, and we're still going to want to play in the river. And these are decisions that as scientists we can't help you make. Okay, these are decisions that are made by the public. Looking at 2007 and how this compares to the records, the hottest temperature ever in Missoula was recorded July was 107 degrees Fahrenheit. We had the warmest night ever at 71 degrees Fahrenheit. That's reminding me of home, which is Mississippi, when temperatures only go down to 71 at night. The average temperature was 78.1 degrees Fahrenheit, or about 11 degrees above average. And this breaks the old record by 3 degrees. So the old record was 8 degrees Fahrenheit, approximately. We had the most number in July of 100 degree Fahrenheit days at 11. 1936, we had 6 of them. The most number of nights, 60 degrees Fahrenheit and above, at 18. 1985 had the old record with 10. So we're not only breaking old records, we're smashing them. We also had the driest July on record at the airport at 0.03 inches. The old record was 0.09 inches. And we couldn't find the date for that. So July this year was a very interesting year, and it could be an indication of what's to come. Now, I will caution you, and I will say that 1 year does not climate make. Okay, these are weather patterns, but we see these trends continuing into the future based on the knowledge that we have in the area. If we go to the climate projections, we see that all year round, we're looking in our area at about 3 degrees C warmer, or 5.5 degrees Fahrenheit warmer. Okay, that's in this. So we're looking here at about 3.5 degrees C, and here as well, approximately on average. But what we're seeing in the wintertime is we're going to be wetter in the winter. And we're going to be about the same or drier in the summer. And this is going to be the thing that's really going to determine where Montana goes. If we stay wetter in the winter, that's a good thing, perhaps. But if we get drier in the summer and we're still warmer, what's going to happen? This is just another way of looking at that graph that I think really helps. This blue line marks the historic variability. Where's it been in the past? So if we look at temperature, the historic variability for annual average temperature has been pretty low. By 2090, we're going to be outside our current level of natural variability. And with precipitation, we're going to be in the same area of precip. So even though we're getting hotter temperatures, we're still not going to get significantly more rainfall here. So if we see this happening in the future, and we see most of this happening in the winter, what we expect is shorter, milder winters with earlier snowmelt continuing, longer growing seasons with decreasing summer stream flows. We're liable to have more drought and fire danger, but this is going to depend on what happens to precipitation. And the ecosystem trends that we'll find, we'll be able to plant our crops earlier. We'll be able to start planting apricots and things like that we haven't been able to have up here before. We'll have more productivity in our forests and crops and rangeland, provided that we can get the precipitation to maintain them. We'll have decreased deer and elk winter kill. We don't know what's going to happen to hibernating animals. They're liable to get a little confused, but nobody's really studied what's going to happen to them. And I'm not going to go out and ask them. We're looking at increased forest insect and disease trends, particularly with pine bark beetle. And we're looking at aquatic ecosystem degradations with high water temperature and more stream closures. And that's going to lead to more aquatic recreation limits. And those are the things that we expect based on the current trends and based on what we know about the science at this time. Thank you very much. How did I do?
Thank you, Faith Ann. One of the other components of this series we thought to instigate our conversation is to invite one of the local clergy to come up as a first responder just for several minutes to just throw out some initial responses and questions as a From a theologian, as a person coming from a faith community, Faith Ann is a member of Emmanuel Lutheran Church, and we've invited Pastor April Jordan, the pastor of that church, to come up as our first responder. So please come on up.
Well, thank you for inviting me here, John. Did you go back over there? And I appreciate the chance to think about this, as I don't often do that, really, very, very much, and just hear about it and talk about it in smaller circles. But to hear Faith Ann's talk today is just wonderful. It's very, very helpful. I want to read some words that may sound like a scientist's prediction for things of our world about 100 years from now, or maybe longer, albeit in a little more poetic fashion. And just listen and let these soak in after you've heard what Faith Ann has had to share with us. I looked on the earth, and lo, it was waste and void, and to the heavens, and they had no light. I looked on the mountains, and lo, they were quaking, and all the hills moved to and fro. I looked, and lo, there was no one at all, and all the birds of the air had fled. I looked, and lo, the fruitful land was a desert, and all its cities were laid in ruins before the Lord. It seems to me those words just describe poetically what Faith Ann has shared with us about the scientific reality of global warming. But these words come to us from the book of Jeremiah, from the prophet Jeremiah, who had the unfortunate job of being God's mouthpiece to a people who didn't want to hear from him, didn't want to hear God's message. And for 40 years, now think about that, for 40 years as regards to how long scientists have been talking to us about global change and studying the effects of, like, CO2. What was the doctor's name, that scientist in 1928 that started, or the one that was collecting data about CO2? Yeah. So it's been time and time and time, and with Jeremiah, it was 40 years he kept talking to top officials and giving them a warning about what would happen if they didn't take heed. And they refused to take heed and hear the warning that they need to make right their relationship with God and with one another. And they wouldn't listen to that. And he kept bringing a warning that disaster would be upon him. And this was one of his nightmare visions. This is what it looks like, and it came true. One of the little comments on this little passage is this, that Jeremiah used words from Genesis to describe the effect of the Israelites' sin. It was as though the Israelites were carrying the earth back to the chaos before creation, destroying all the beauty and order that God had made. Interesting way to think about it. Israelites' sin they were working to carry us backwards. And that's an interesting thought to think about. How is our sin carrying us backwards to chaos and making ruin of what God has created and put in our care? The sin of the Israelites was to not take God seriously. George Murphy is a physicist and an ELCA pastor, a Lutheran pastor. And I just happen to know the guy in seminary. We went to the same seminary, so whenever I see his articles and so forth, I perk up and read them. And he made the comment in a recent article that perhaps one of the reasons we as a faith community don't take this issue seriously is we have a resistance to it because we too don't take God seriously. that is the consequences of our actions, that maybe we were thinking that the promise is that God will always take care of us, so therefore, we don't have to take any of this seriously. And of course, texts like this and other stories in the Bible point to the fact that our actions have consequences, and that we don't get to just fit God into our life whenever it's convenient, and that all of the promises are true. All of the promises are true. So I just lift that out to you, just that one point to think on in your conversations together, as maybe one of the starting points is, do we as a faith community take this aspect of it seriously, take our role seriously as those who are God's people, called to respond to these facts, and called to be in relationship, a serious relationship with God, with the earth, and with one another. Thank you.
Thank you, April. At this time, I would like to invite us to have some conversation around each of our round tables. And in this conversation, the temptation will be to get to solutions and what can we do right away, but let's wrestle, let's think about, what are our initial reactions when we hear this talk, when we think about the science. Let's see if we can stay in that conversation. What are some of the questions that we have as we listen to this? What are some of the rebuttals that we might wonder about? I mean, is this really true? Let's just throw any of that out there. And what comes up to you? Let's make sure in each table there is someone who is a moderator to make sure that every person has a voice within the table, and that it's a shared open conversation amongst everybody. Let's take about 15 minutes, and then we'll come back and have a chance to talk in the larger group. So I invite you to talk. You might want to introduce yourselves and have some initial conversation about this. I'll invite us to bring our attention back to the whole group. We want to have an opportunity for the tables to ask in particular questions or to respond to what we've heard tonight from Faith Ann. And the first thing, there were a few tables that were wondering about, in a sense, saying, okay, if the climate is changing and the Earth is warming, but is this really human caused or not? Is there other natural occurrences that might be happening that we're just happen to be seeing here, and we're going to experience it all together, but we wouldn't say it's really our fault or our causation. And so Faith Ann hit on that some, but there's a few different rebuttal arguments that are more typical, and we thought maybe a few minutes to pay attention to those. So thank you.
Okay, I'm back on the spot again. The first thing I wanted to say was that there are a lot of confusing statements out there. And there are a lot of confusing people out there. And there are people on both sides of the issue who are very, very good people. And none of anything that I say tonight is supposed to be denigrating anybody. And I want to make that clear up front. The other thing is that in 2003, there was a paper in The Science, which is one of the top 2 peer-reviewed journals in science. And that's one of the things that if you're a scientist and you really want to know you've made it, you want to get into either Science or Nature. Those are the 2. And in 2003 in Science, there was a paper published where they did an analysis of 10 years of papers, and they did a search on global climate change and said, okay, out of this they found 928 abstracts that had to do with climate change. Of that, none of them disagreed with the fact that climate change was occurring. Okay. So that's the first thing. In the peer-reviewed journals, climate change is happening. And the few times that we bring up provocative papers, we're either able to rebut them fairly quickly, or they're thrown out there just to stir the pot.
You mean human cause
Climate change.
Just climate change?
Just climate change at this point in that paper. They weren't talking about human-caused climate change in that paper. It was just, is climate change occurring? She didn't get that specific in the paper. The second part of that is it human-caused? So are we to blame? Me just as much as anyone else. And so I wanted to dig up a couple facts before I started spewing statistics out there. And I think I just want to read this. This comes from the IPCC report that was put out this year. This is from the frequently asked questions of Working Group 1. And I won't read all of it. It says, are the increases in atmospheric carbon dioxide and other greenhouse gases during the industrial era caused by human activities? And the answer, yes. The increases in atmospheric carbon dioxide and other greenhouse gases during the industrial era are caused by human activities. In fact, the full observed increase in atmospheric CO2 concentrations does not reveal the full extent of human emissions, in that it only accounts for only 55% of the CO2 released by human activity since 1959. In all cases, atmospheric concentrations of greenhouse gases and their increases are determined by the balance between sources and sinks. So things that we know, we have a very good handle on fossil fuels that are burned every year. And we have a very good idea, a fairly good idea of how, where things are going once they leave there. And fossil fuel combustion, plus a smaller contribution from cement manufacture, is responsible for more than 75% of human-caused CO2 emissions. Land use change, primarily deforestation, is responsible for the remainder. For methane, another important greenhouse gas, emissions generated by human activities exceeded natural emissions over the last 25 years. And then to go on down a little bit, on average, present-day tropospheric ozone has increased 30% since pre-industrial times, and the increase results from atmospheric reactions of short-lived pollutants emitted by human activity. The concentration of CO2 is now 379 parts per million, and methane is greater than 1,774 parts per billion, both very likely much higher than any time in the last 650,000 years, during which CO2 remained between 180 and 300 parts per million, and methane between 320 and 790 parts per billion. The recent rate of change is dramatic and unprecedented. Increases in CO2 never exceeded 30 parts per million in 1,000 years, yet now CO2 has risen by 30 parts per million in just the last 17 years. So at least in this, the studies that they've done demonstrate that the CO2 increases in the atmosphere are caused predominantly by humans. First through fossil fuel emissions and then through land use change. And we've been fortunate in that a good portion of that so far has been absorbed either by the oceans or by the land, but that's not going to be able to continue into the future because things are starting to change. And that's kind of a different topic there. But so far we've been lucky in that regard. Are there any other questions? The other question was, how do we determine that the CO2 in the atmosphere comes from humans? First, we know that it's sources and sinks. The other way is we can actually do a chemical analysis of the CO2. And we know the chemical makeup of the CO2 emitted by plants, and we know the chemical makeup in fossil fuels. And if you compare that to what's actually in the atmosphere now, you can see that it's much more heavily weighted towards the fossil fuels. And that's why we know that the fossil fuels are the ones that are predominantly causing the increase. Yeah.
So in regard to that, what do you think about the coal-fired plant that the governor is pushing forward with coal, like the sequestration of the, and how do you respond to that in terms of what this will do to climate change?
Okay, the question was, how would I respond to the governor's coal-fired power plant and his sequestering of the CO2 in clean coal, I believe is what he's calling it, is clean coal. And from a scientific standpoint, I have to say that the technology has promise, but anything that you put into the ground through a pipe has a chance of leaking out. And they're going to have to demonstrate to me pretty hard, clear, and fast that that CO2 is not going to leave the earth before I would believe that that's a truly viable long-term option.
One of the discussions that goes on among this group of scientists even is where is the point of no return?
Right. Where's the point of no return, or have we even reached that? 5 years ago, they told me 10 years. We're still saying 10 years. We don't know where that tipping point is. And that's one area of very active research. A person who may have a much better handle on that than I is Dr. James Hansen, who'll be here October 22nd. Let me plug him. He'll be here on October 22nd and giving a lecture here at the university. And he's been in this field a lot longer than I have, almost as long as I've been alive. So I'm going to defer that one to him. Yes?
I've noticed in a couple of, maybe it was in the newspaper, or a couple of magazines at this time, some source that there was an indication there were people who thought that climate change was caused by sunspot activity and it had to be at the highest right about now. And there was a comment in some magazine recently that they've proven that the sunspot activity is not the cause of the rapid increase global warming. But most of it is by activity. Now, you respond to that at all? You know anything about that science?
Actually, I'm in luck on that question. So for those of you who didn't hear, the question was that there was an article in a magazine, Time or Newsweek, he wasn't really sure, that stated that sunspot activity was at its peak right now, and that was actually responsible for a lot of the climate change that we're seeing, was these changes in sunspot activity. But yet there was another article that said that they had shown it hadn't. There was actually a scientific article published about 3 weeks ago, I believe, that showed that sunspot activity is actually so small in the amount of change of energy that comes to the Earth that it couldn't possibly have an impact on climate change. Certainly not to the rate that we're seeing. And there's no way that it could account for what's going on. Yes?
One of the questions that came up here was out of a recent NOVA show that talked about solar dimming and the impact of that on climate change.
Okay, sure. This was about the recent NOVA special on global dimming, which has been on 3 or 4 times now on NOVA, and I've shown it to a couple of classes. It's a really good show. And actually what the premise of the show is that the pollution that we've emitted, particularly sulfates, have actually cooled the atmosphere and dimmed the sun and reflected a lot of the energy back into space. And the premise of the whole thing was that it was actually masking what we were doing to climate. And you'll notice that about the time that we really hit hard on pollution with the Clean Air Act and things like that, a few years later, we notice a sharp shift in the curves of our temperature responses. And so we think indeed that global dimming, through this reflection through our pollution, was actually masking the full effect of climate change. And so one of the kind of off-the-cuff solutions that people are recommending is we just put sulfur back in the atmosphere, sulfates back in the atmosphere, but then you've got the acid rain issue again. So that was definitely said tongue-in-cheek. But certainly I believe that global dimming did happen, particularly during the 50s through the 70s, and that did mask the true effects of climate change during that time.
Here's another question.
Okay.
Gary wanted to jump to solutions, but tried to hold back. But did wonder if in all the study of climate change and the impact of greenhouse gases, whether there are some silver bullets, I guess, that science has recommended in terms of our response to begin to reduce those greenhouse gases.
You guys are hitting me from all sides tonight. Let's see, are there any silver bullets in response to solutions to climate change? I'll go back and start by saying that I feel that in this series, I'm the climate change bad guy. I give you guys the science and what's out there, and I don't get to talk anything about solutions or anything else. Having said that, there's not one single thing that we have out there. Technology is great, it's growing by leaps and bounds, but from everything that we've seen so far, it's still going to take humans changing their lifestyles in order to reduce the CO2 levels to the levels that we feel we need to get them to. And David Merrill, I'll pick on you. Do you have anything to add to that? Come on.
Actually, I can just. My name is David Merrill. I'm the director of a national network that's based in Missoula called globalwarmingsolution.org. And we've been working on a paper for about 3 years, and we released it in July. It's on our website, and it presents a 15-year rapid energy transition. It shows how we can move from our current system, which is about 85% fossil fuels, to a system that's largely renewable energy over a 15-year period. It'd be like a wartime speed mobilization, and it's been favorably reviewed by 2 of the top energy analysts in the country. So it's on our website, globalwarmingsolution.org. You can check it out. It's a good read, and if you want to just start with the executive summary, that's a few pages, and I'd love to hear your comments. But there is a tremendous amount. It's very hopeful on the technology side.
Okay. And that was Global Warming Solutions with an S? Singular. Globalwarmingsolution.org. No S on that one. Yes.
And are there models out that would tell us if we can reduce our CO2s in 50 years, how much of a difference that would make as far as these trends, or if we reduce it in 15 years, or, I mean, are there predictions?
The same models that we use to predict what's going to happen in the future, we can play games with the CO2 concentrations. And actually, they did that as part of the IPCC report. And what you do is you set a whole bunch of different scenarios. You set business as usual, and you can set very conservative ratios. And they did a range of, well, the ones between there, and projected this is what happened should we follow each one of these trajectories. So they do that information, and it is out there. So.
Is there a website we can?
What I would do is go to the IPCC website and look at there's a paper, Working Group 3 is on mitigation and strategies, and they would be the ones that would demonstrate some of that. And their summary for policymakers is actually it's very thorough, but it's also a fairly easy read because it's made for policymakers who are not scientists. Not denigrating policymakers, but they're not scientists. So we're having to talk to people outside of our little network. And so they're fairly easy to read, and I would encourage you to look at those. Yes?
I have a question about the Freon that's used in refrigerators and air conditioners, and also the aerosol spray cans. For one thing, I don't understand how or at what point the Freon is released. Is it during the time that the consumer, the person, owns the refrigerator? Is it somehow released then, or is it when it's taken to the dump? Or is it when it was made, manufactured, as far as the refrigerator is concerned? And then I don't understand how the aerosol sprays, how just those little aerosol sprays can make an effect.
Okay. This was a question about the Freon and the CFCs that were in aerosols, and how they might have been released was the question. And the answer to that is, in the 1980s, in the Southeast, we had notoriously big hair, and that took a lot of hairspray. Okay, and there were still CFCs in the hairspray cans, and that's a little tongue-in-cheek, but certainly millions of people using hairspray cans had an impact. The larger impact came from leaks in systems. Car air conditioner systems develop leaks over time, and the Freon leaks out, and you just recharge it, and then it leaks out again. Refrigerators, the same thing, they'll leak over time, or when they were thrown in the dump, that when we didn't realize the impacts of the CFCs, we weren't careful about recycling them. And so we didn't take care of where we were putting them, and they ended up in the atmosphere. And now that we've gone to alternatives, that's not as large of an issue anymore as it was in the past. But it was just natural leaks within the manufacturing process while it was being used and then after it was thrown away. So it was throughout the process. They're just leaks that happen. When you're dealing with a gas, there's going to be a leak.
Let's thank Faith Ann. Good question. John told me to give you guys a teaser for next week. I don't know how I'm going to do that. But I would have to say that the Western Montana Spiritual Development Council, we did want to do a more sustained effort on this. In other words, a sustained educational effort that would really give some meat and some real foundation for the way you think about these issues. My task next week is a little bit like Faith Ann's. Faith Ann talked about the way it is. That's what science is about. It's the way it is, right? I'll talk about the way it ought to be. In other words, that's the domain of ethics. We talk about the way the world should be, the world ought to be. But I'm not going to tell you what to do. That comes right at the end, the last three speakers. I chose to be an ethicist and not a preacher because I didn't feel like I could tell people what to do. Although that's not what that's a joke. They just like to provoke you, right? But my task next time is to lay out the ethical issues, of which there are many and complex, that arise from global climate change. And I think it's a complex picture, and hopefully I can simplify it a little bit and lay out the ethical issues that you should consider. And I will try to, as much as possible, put that in a faith context as well. So hopefully come out, bring your friends, and keep them coming to all of these, because remember, the last three ones are where the real payoff comes out. Okay? Thank you.